Let's go over the answers to pages 144 to 150 in Module 3. Again, we're working on linear equations, the equations of lines, and we are taking these two-step linear equations from word problems, from sentences, to equations, to tables or charts, and to graphs. If you're given any one of the four of those, the goal is to be able to transfer it into one of the other three forms. So again, if you're given a table, can you turn it into an equation, a graph, and a sentence, and so forth. I had previously, on page 144, I had done the equation with you to round stacks of containers, but I left you to do the square ones. With the square ones, one square container is 15 centimeters high, and then each additional one you add, so every one you add, it goes up 0.4. So if you add another one plus one more, it goes up 0.4. That's the rate or the slope. When the height goes up, again, we think of slope as rise over run. When the height changes by 0.4, the run, going forward or backwards, changes by 1. So the slope is 0.4 over 1, which is 0.4. And then we have to figure out the value when x is 0 for slope-intercept form. Currently, we have it when x is 1. But that will be the slope. And so plus 0.4 plus 0.4, and we can see when we had 5 containers, we were at 16.6 centimeters. To go to 6 containers, add 0.4. 16.6 plus 0.4 is 17. 17 plus 0.4 is 17.4. And then we would need to get, I could continue this pattern up to 13 containers, or we could just find the equation for this line, plug in 13 for x, and get our y value. Again, square containers, I said let y be the height in centimeters. X is the number of containers. So the total height is the first container, 15, plus the rate, 0.4, times the number of containers. Oh, but we have to take out the first one because the first one is a different height than the rest. And so our equation output, y, is 15 plus 0.4, open parentheses, x, which is our input, the number of containers, take away the first container. Well, we need to distribute. So I'm going to multiply that 0.4 into the parentheses. Y is 15 plus 0.4x, that is 0.4 times x, minus 0.4. And up above, 0.4 times negative 1 is negative 0.4. Mathematically, we often skip this step because we'll eventually just do it in our heads, but for right now I want to show it, and that is the commutative property of addition, because we need to put the like terms next to each other in our order of operations. So I'm going to trade places with these two terms. So y is 0.4x plus 15 minus 0.4. Combined like terms, 15 minus 0.4 is 14.6. Y equals 0.4 times x plus 14.6. This is now in slope-intercept form. Y equals mx plus b. This means that our slope, as we described previously, is 0.4. And where this line, if it were drawn straight as a linear equation, it would have crossed the y-axis at 14.6. So that means when x is 0, and again, 0.4 times 0, so if I put a 0 in, all I'm going to do, I'm going to cover that term because it's just zeroed out, and you would have y equals 14.6. So when x is 0. Well, for problem 13, for the problem with 13 containers, let's put a 13 in for x. Y equals 0.4 times 13 plus 14.6. I'm just using the equation we set up above. Y equals 5.2 plus 14.6. 5.2 plus 14.6 is 19.8. And so we used an equation to find the height for 13 containers. And we can use that equation to find the height of any number of containers or to find the number of containers for any height. So it is, I find, very convenient to turn sentences, graphs, or tables into equations. On the next page, they asked us to graph the square containers. I did mine in blue. And so when there's one container, how high is it? 15. So up here on my height, that's where 15 would have been. And then when there's two containers, it's at 15.4. 3 containers, 15.8. 4 containers, 16.2, and it just continues. And it's going to form a straight line that would have crossed the y-axis at 14.6 if, in slope-intercept form. And you can look at these two lines and see that somewhere out here, the height of the brown containers will get taller when there's the same number of containers. There's a point of intersection because the round containers have a steeper slope, so they're rising faster, a steeper line. Again, the steeper the line, steeper the slope, the faster it rises. And this square container is a shallower line. It's not as steep, so it's rising more slowly. And so we put those on, and we should have the rest of this page. We had done that previously. And problem 5, page 146. Consider the stack of square containers. Let C be the number of containers in a stack of square containers. Let H be the stack height. Write an equation that gives the stack height in terms of the number of containers. This was the same equation that I used before where I had used Y and X. In this case, they're just asking us to use an H and a C. Okay, so H is stack height, C is containers. The stack height is the first container, 15, plus its rate of change. It goes up 0.4 for every container added after the first container. So I have to subtract that first container away because it was a different height. So H equals 15 plus 0.4, open parenthesis, C minus 1, close parenthesis. Use your table, graph, or equation to determine the stack height of 6, 7, and 13 containers. I've already done that. I already have 6, 7, and 13 containers, so I just put my numbers for problem 6. 6 containers was 17 centimeters, 7, 17.4, 13 was 19.8 centimeters. Analyze the equations you wrote for round and square containers. How are these two equations you wrote similar? Why are these equations similar? Explain reasoning. Well, for my round container, height was 9, height of one container was 9, plus it had a rate of change. It grows by 0.8 centimeters per container after the first container. For the square containers, the height is 15 centimeters, plus a rate of change of 0.4 after the first container. These two equations have the same structure. They're both set up in the same way, but they differ with their constants. Again, the constants of 9 is different than 15, and the rate of 0.8 differs from 0.4. And so they have a different starting heights and different rates of growth. And I guess that's a part of the answer to part B. How are these equations you wrote different? Why are these equations different? Explain. The numbers 9 and 15 from the two equations represent the height of one container. The numbers 0.8 and 0.4 represent the amount that each stack grows when you add one container. And so they're going to start at different rates and grow at different rates. The equations you wrote for the heights of the containers can be written in equivalent forms. rewrite each equation in the form, slope-intercept form. So y equals ax plus b, or output is slope times input plus starting value. So for my round container, I set it up right here. And again, for both of these, let y be height, x be number of containers. For round containers, output is 9 plus 0.8. Number, x is number of containers after the first one. And I'm just going to simplify this equation. My first move is to distribute. My next move is commutative property of addition. Combine like terms, and I have my equation. Similar for square containers, I set up my original equation. I distribute. I'm going to commute these two so I can use order of operations, PEMDAS, to combine like terms. I have these terms next to each other so I can combine them, and I simplify. And I end up with these two slope-intercept form equations. Explain what the numbers in the equations mean in terms of problem context. I actually answered that one down here. The 0.8 and 0.4 represent the change in height as another container is added. The 8.2 and 14.6 show where the graphs would intersect the y-axis if they were drawn as a straight line. It's a little bit, we're drawing these in slope-intercept form, we're describing them, but in actuality they really wouldn't be, because if you had 0 containers, you would have 0 height. And according to this equation, if you had 0 containers, you'd have 14.6. So this equation really doesn't represent the 0 value. It shows it in slope-intercept as if it were drawn as a straight line. We'll get to more of those in a bit. It might not make perfect sense right now, and that's okay. But just realize that if you had 0 containers, you'd have no height. According to this equation, if you had 0 containers, you'd have 14.6 centimeters height. And then refer back to the graphs, explain how the numbers in these equations and your graphs are related. The 0.8 and 0.4 represent the slope of each linear equation, or the rate of change. The 8.2 and 14.6 represent where the lines, I should have said, would have intercepted the y-axis, and especially, again, if they were drawn as straight lines. Each of these values, with the round containers, when it's 1, it's set up right here at 9, 2, 3, 4. According to slope-intercept form, the 0 value would be, again, part of that straight line would be right there. And the 0 value for square containers would be over here. But really, it's not the case. The 0 values would have been down here. So these graphs would have gone up and then across. They wouldn't truly be linear if we drew them as they really appear in real life. But by drawing it or representing it with a linear equation, it's easy to find all the other values in very few steps. All right, let's take a look at page 147. Use your equation of the form y equals ax plus b to calculate the stack height. So again, for round containers, this was my equation. And for square containers, this was my equation. 2 dozen round containers. Well, 2 dozen is 24, so I'm letting x equal 24, and then simplifying this equation. And so I plug in an x, I multiply, I add, and I get y equals 27.4 centimeters. How about 2 dozen square containers? I'm using the square container equation, putting 24 in, and simplifying, and I get y equals 24.2. What height should Storage Pros make its boxes to accommodate the height of a stack of 2 dozen of either type of container? So you only want one box, and you want it to be able to hold the containers that are taller. So if you're talking 2 dozen, which of these is taller? Well, the round containers. So the box has to be able to accommodate this height. If it can accommodate 27.4 centimeters, it will accommodate 24.2 with just a few centimeters left over. So they would need to make their boxes big enough to accommodate 27.4 centimeters of containers, so the round containers. And again, if your answers are worded differently, it's fine. And if the problem originally didn't make sense to you and now it does, that's okay as well. If it doesn't make sense, though, please get a hold of me and let me know. If even after you look at this and listen to this, I don't understand where these numbers are coming from, talk to me. We'll set up a Google Meet and figure it out. Number 10. Storage Pros had extra boxes that were 45 centimeters tall. How many round containers could fit inside the box? Well, 45 centimeters is the Y value, so I'm using the round formula, Y equals 0.8x plus 8.2, and it's the Y value that's 45 in this case, the height. So I substitute 45 for it. 45 is 0.8x plus 8.2. Subtract 8.2 from both sides. 36.8 equals 0.8x. Division property of equality. Divide both sides by 0.8. And 46 containers is x. So it can hold 46 round containers. How many square containers would fit inside? We're going to do the same. We're just using the equation for square containers and changing this y to a 45. 45 is 0.4x plus 14.6. Subtraction property of equality. I need to get x alone, so I'm going to subtract this positive 14.6, and whatever I do to one side of the equal sign, I'll do to the other. That leaves me 30.4 equals 0.4x. Well, x is being multiplied by 0.4, so I'm going to divide both sides by 0.4 to turn that into a 1. 0.4x divided by 0.4 is 1x. 30.4 divided by 0.4 is 76. So you could fit 76 square containers in a 45 centimeter box. Let's take a look at page 148. I started that one with you. This was using slope-intercept or the equation where the first height is different. And so Limousines by Lilly, we did that one already. We did transportation with class. We did round containers. I left you with square containers, and the formula for square containers, the original height, or the height, is the height of the first container, 15, plus 0.4 containers after the first, minus 1. Because, again, it goes up 15 for the first container, but all additional ones go up 0.4. So I have to get rid of that first term for this equation to work. When I simplify it, I get y equals 0.4x plus 14.6, and that was the equation we were using. Use your equation to explain the meaning of C and D in terms of y equals C plus D, open parenthesis, x minus 1. C is the amount per unit. It's the rate for one. So if you only have one, in this case the first one, that's it. And then D is the amount per additional unit, or rate or slope. How much it rises or falls in height, depending on, after you add the first one. Use your equation to explain the meaning of A and B in terms of y equals ax plus b. Well, in this case, A, in slope-intercept form, this would be the letter M. It's the rate of change. It's the slope. So again, A represents how much it goes up or down in the slope changes per every unit, per move. And B is amount per 0 units. It's the rate at 0, or where this crosses the y-axis. So when x is 0, you put in a 0 in for x, and you solve your equation, y equals that b value. Page 49. Refer back to the graphs of the plastic containers and the related equation. Explain if and how the two equations of the form y equal ax plus b can be visualized on the graph. And I went y equals ax plus b. Again, a is the slope or the rate of change, often called rise over run. Rise, how far it goes up or down. So a change in y value over run, a change in x value. Is it going forward, positive x, or backwards, negative x? Take a look at, I just did a line, and I wrote the equation y equals 2x minus 4. This minus 4, that's the b of y equals mx plus b. So negative 4. This line crosses at negative 4. That's right here, where the line crosses the y-axis at negative 4. And then what's the slope of this line? The slope is 2, which is 2 over 1. That means it goes up 2, forward 1. So to go from point to point, we're at negative 4, negative 3, negative 2, up 2, forward 1, from 0 to 1. That point is on the line. And then let's do it again. Up 2, 1, 2, forward 1. That point's on the line. Up 2, 1, 2, forward 1. Up 2, 1, 2, forward 1. Up 2, forward 1. Or I could also, because again, negative divided by negative is positive, negative 2 over negative 1 equals 2 over 1. So I could also go down 2, back 1, down 2, back 1. The slope in this case, because 2 is the same as 2 over 1, but it's also the same as negative 2 over negative 1. And every point, any value you put in for x is going to spit out a y on this line. Which equation, which form of a linear equation do you prefer and explain? This is completely up to you. I like slope-intercept form. I prefer linear equations written in slope-intercept form, because then all I have to find is the slope and the y-intercept. I just have to find this value, and then I just have to find the rate of change. And I can figure out how y has changed and how x has changed. If you give me 2 points on a line, I can figure that out very easily. And so this form makes it easy to graph equations, find exact values, and create tables. That's why I like it. Back to limos, page 150. At the beginning of the lesson, you wrote equations for a fee schedule for limousines by Lilly and transportation with class. Determine which graph represents each equation and use your equations to explain your reasoning. Well, let's take a look at, I'm going to go back to that page as well, I think. Here we are. So, limousines by Lilly. The first hour was $99. Transportation with class, the first hour was less. And when we wrote these in slope-intercept form, again, that still held true. So this is less than this. So line M has a lower start than line N. N starts off more expensive. That's limousines by Lilly. Since the price starts off more expensive, but then it has a lower cost for each additional hour. So line N has, since it has a lower cost, has a shallower slope. It's not as steep. And line M is transportation with class. It will start off cheaper, but because it has a steeper slope, it gets more expensive. So totally different rates. Suppose Katie decides to charge $124.99 for the first 3 hours, and then $49.99 for each additional hour. Write an equation to represent Katie's fee schedule. Well, so her fee is $124.99, and again, this is for 3 hours. And then her rate per hour is $49.99, but it's after 3 hours, so I'm going to subtract a 3. So y equals $124.99 plus the rate $49.99 for each hour after the third hour, minus 3. And that is problems pages M3 144 to 150. So if it makes sense, please take the assessment on Edulastic to show your knowledge. And next week we will go into the next section. Good luck.